current and circuit.
When water flows in a river from a higher level to a lower level, forming waves, it is called a current of water. Similarly, if we make electric charges flow by applying a force, a current of charges is created. The flow of electric charges under the action of a force constitutes electric current.
Activity: take a torch, take out its cells, and try to obtain light. Is it possible to get light? No. Can you tell why? This is because cells are the source of electricity, which makes the bulb glow. Take two small copper wires and join its ends to a small bulb. Join the other two ends of the wires to a dry cell. Observe the bulb. The bulb glows. Here the electric current generated by the dry cell flows through the copper wires and hence through the bulb. The current passing through the bulb makes it glow. Take out any one end of a wire connected to the cell. Observe the bulb. The bulb does not glow since one end of the wire is disconnected from the cell. This shows that the wires should be connected between the cell and the bulb to make the bulb glow. Hence, a closed path is required for the current to flow in the wires and the bulb. The closed path through which electric current flows is called as a circuit. Let us understand what makes the electric current flow in a circuit.
Matter is composed of atoms, and every atom has protons and neutrons present inside its nucleus. While the electrons revolve around the nucleus in their fixed orbits, only electrons can move from one point to the other, unlike protons and neutrons, which are fixed inside the nucleus. In some substances, like metals, the electrons in the outermost orbit are loosely bound to the nucleus and can easily be detached from the atom. These electrons move randomly in all directions and are called free electrons. When a force is applied and these free electrons are made to flow in a particular direction, they constitute electric current. It is interesting to know that metals contain a large number of free electrons moving randomly in all directions, which are readily available to constitute electric current. Electric current is defined as the rate of flow of charges. It can also be defined as the amount of charge flowing through a conductor at a given point per unit time. If Q is the net charge flowing through any cross-section of a conductor in time t, then current I is given by I is equal to Q upon T. The SI unit of charge is coulomb and is symbolically represented as C. The SI unit of time is second. Hence, the SI unit of electric current is coulomb per second or ampere, which is named after French physicist
André Ampère.
The instrument used to measure current is called an ammeter. The electric current in a conductor is said to be 1 ampere when a charge of 1 coulomb passes through a given point in 1 second. That is, 1 ampere is equal to 1 coulomb upon 1 second.
Small values of currents are expressed in milliampere and microampere. 1 milliampere is equal to 10 to the power minus 3 amperes. 1 microampere is equal to 10 to the power minus 6 amperes. While large values of currents are expressed in kiloampere and megaampere. 1 kiloampere is equal to 10 to the power 3 amperes. 1 megaampere is equal to 10 to the power 6 amperes.
Direction of electric current. When electricity was invented, scientists were known that there are two types of charges, positive charges and negative charges. But during that time, electron was not discovered, and it was believed that electric current results only due to the motion of positive charges from a positively charged object to a negatively charged object. This direction of flow of charges was thus taken as the direction of electric current. Thus, the direction of conventional electric current is taken from the positive terminal of a cell to the negative terminal through an electric circuit.
Drift speed of electrons. At room temperature, the free electrons in the metal wire move randomly in all the directions when no electric source like a dry cell or a battery is connected to the wire. When a source of electricity like a cell or a battery is connected between the ends of the metal wire, an electric force acts on the free electrons present in the wire, making them to move towards positive terminal of the cell or the battery. The electrons gain velocity in the direction of the electric force. This velocity gets superimposed on the random velocity of the electrons. As a result, the electrons in the conductor move with a certain average drift speed towards the positive terminal of the cell or the battery. This flow of electrons constitutes the electric current in the wire.
Let us solve some numerical problems based on the topics we have studied.
Problem 1. A current is of 0.2 ampere is flowing through a bulb for 5 minutes. Find the charge that is flowing through the circuit. Solution. Let us first write given quantities. Current I is equal to 0.2 ampere. Time T is equal to 5 minutes, which is equal to 5 into 60 seconds, which is equal to 300 seconds. We have to find total charge Q flowing through the circuit. It is given by Q is equal to I into T. Substituting given values of current I and time T, we get Q is equal to 0.2 multiplied by 300. Therefore, Q is equal to 60 coulomb. Hence, the charge flowing through the circuit is 60 coulomb. Problem 2. A charge of 420 coulombs is flowing through a circuit for 10 minutes. Find the current in the circuit. Solution. Let us write the given data. Charge Q is equal to 420 coulombs. Time T is equal to 10 minutes, which is equal to 10 multiplied by 60 seconds, which is equal to 600 seconds. Let us find the current I flowing through the circuit. It is given by I is equal to Q upon T. Therefore, I is equal to 420 divided by 600, which is equal to 0.7 ampere. Therefore, the current in the circuit is 0.7 ampere.
Problem 3. Calculate the number of electrons constituting 1 coulomb of charge. Solution. We know that the charge of an electron is 1.6 into 10 raised to minus 19 coulomb. Now, if charge is 1.6 into 10 to the power minus 19 coulomb, then number of electrons is equal to 1. So, if charge is 1 coulomb, then number of electrons is equal to 1 upon 1.6 into 10 to the power minus 19 into 1, which is equal to 10 to the power 19 divided by 1.6, which is equal to 10 divided by 1.6 into 10 to the power 18, which is equal to 6.25 into 10 to the power 18. Thus, 6.25 into 10 to the power 18 electrons taken together constitute 1 coulomb of charge. Electric potential and potential difference. Have you ever thought what causes an electric current to flow? Let us perform an activity to understand about flow of charges and potential difference.
Activity. Take 2 water tanks having taps near their bottoms and label them as tank A and tank B respectively. Keep tank A at a higher level than tank B. Mix some color in the tank A. Connect both the tanks using a transparent pipe. Turn on the tap and observe the setup carefully. What do you observe? Well, you can see the water flowing in the pipe from tank A to tank B. Can you explain why the water is flowing from tank A to tank B and not from tank B to tank A? Well, the water in tank A is at a higher level, which means a point of greater potential energy than in tank B, and water flows from a higher level to a lower level. When the water in both the tanks come to the same level, the flow of water stops. Hence, for the water to flow between the two tanks, there should exist a difference in potential between the two levels. In the same way, current flows on account of difference in electric potential between the bodies. When positive charges accumulate on a body, it is said to be at higher potential. If we connect this body to an uncharged body, or a body with lower potential, with a metal wire, there would be a flow of charge. Hence, there should exist a potential difference between the 2 points for an electric current to flow between them.
Electric potential at a point is the electric level at that point. If there is a difference in the electric potential at 2 points, we say that there exists an electric potential difference between these 2 points. To elaborate this concept, let us consider a copper wire connected in the form of a loop. Is there any current flowing in the wire? No. Can you guess why? This is because charges move in random directions such that there is no net transfer of any charge across the conductor. Here, all the charges are at the same potential. Now, let us connect a battery with the copper wire. The end of the copper wire connected to the positive terminal of the battery is at a higher or positive electric potential, and the end of the wire connected to the negative terminal of the battery is at lower or negative electric potential. That is, there is an electric potential difference between the two ends of the wire. Hence, a current is set up in the wire as soon as the battery is connected to the wire. In other words, the battery creates a potential difference between the ends of the loop, and as a result, a current is set up in the loop.
Electric potential difference between 2 points in an electric field is defined as the amount of work done to move a unit charge from one point to another point. Hence, potential difference V between 2 points is equal to work done W upon charge Q. That is, V is equal to W divided by Q.
Potential difference is abbreviated as PD. The SI unit of potential difference is volts, denoted as V. It is named after an Italian professor, Alessandro Volta.
Electric potential difference between 2 points in an electric field is said to be 1 volt when 1 joule work is done to move an electric charge of 1 coulomb from one point to another point. Hence, 1 volt is equal to 1 joule upon 1 coulomb. That is, 1 V is equal to 1 J upon 1 C. Small values of voltages are expressed in millivolts and microvolts. 1 millivolt is equal to 10 to the power minus 3 volts. 1 microvolt is equal to 10 to the power minus 6 volts. While large values of voltages are expressed in kilovolts and megavolts. 1 kilovolt is equal to 10 to the power 3 volts. 1 megavolt is equal to 10 to the power 6 volts. The instrument used to measure potential difference is called a voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Now, let us solve a numerical based on potential difference.
Numerical problem. Find the amount of work done if 3 coulomb of charge is moved through a potential difference of 9 volt. Solution. Let us first write the given data. Charge Q is equal to 3 coulomb. Potential difference PD equal to 9 volt. Let us determine the work done W using formula PD is equal to W upon Q. Therefore, W is equal to PD multiplied by Q. Substituting the given values of Q and PD, we have W is equal to 9 multiplied by 3. W is equal to 27 joule. Therefore, the work done in moving a charge of 3 coulombs through a potential difference of 9 volt is 27 joule.
Circuit diagram and symbols used for electrical components. An electric circuit can be represented by means of a simple diagram called the circuit diagram. An electric circuit basically comprises a cell or a battery, a plug key connecting wires and electrical components. In a circuit diagram, various components of the circuit are represented by their standard symbols such as an electric cell. An electric cell provides the necessary electrical energy, that is, potential difference to a circuit. In the symbol of electric cell, the shorter line denotes the negative terminal and the longer line denotes the positive terminal. A battery. A battery is a combination of 2 or more cells which provides large potential difference to a circuit. A plug key or a switch, open. A plug key or a switch in open state allows the flow of current in a circuit, that is, it switches on the circuit. Plug key or switch, close. A plug key or switch in closed state stops the flow of current in a circuit, that is, it switches off the circuit. Connecting wire. A straight line represents a connecting wire between any two components of the circuit. A wire joint. A wire joint indicates that two wires are forming a junction. Wires crossing without joining. This symbol indicates that two wires are crossing each other without joining. An electric bulb. An electric bulb indicates the presence of electric supply. A resistor. It reduces the available current flowing in a circuit. A variable resistance or a rheostat. It regulates the available current in a circuit without changing the voltage source. Ammeter. An ammeter is a measuring device which measures the electric current flowing in a circuit. It is connected in series. Voltmeter. Voltmeter is also a measuring device which measures the potential difference between 2 points in an electric circuit. It is connected in parallel. Ohm's law. In 1827, a German physicist, George Simon Ohm, established a relation between the voltage across a conductor V and the current I flowing through the circuit. Let us perform an activity to understand this relation.
Activity. Let us use a nichrome wire, XY, as a resistance. Nichrome is an alloy of nickel, chromium, manganese, and iron. Connect the wire to a circuit to find the amount of the current flowing through it. When different potential differences are applied across it, an ammeter is connected to measure the current flowing through the wire. A voltmeter is connected across the nichrome wire to measure the potential difference across it. A plug key is used to set the current in the circuit as on or off. Tabulate these observations. First, connect one cell in the circuit. Insert the plug key and observe the current I flowing in the circuit by observing the ammeter reading. It is 200 milliampere. Note the potential difference V across the wire by noting the voltmeter reading. It is 1.5 volt. Now, connect two cells in the circuit. Insert the plug key and record the ammeter and voltmeter readings. They are 400 milliampere and 3 volt. Similarly, connect 3 and 4 cells in the circuit and record the ammeter and voltmeter readings. These readings are 600 milliampere and 4.5 volts and 800 milliampere and 6 volts. Let us plot a graph between V and I. Potential difference V is taken along the y-axis and the current I taken along the x-axis. Mark points representing observations and plot the graph. It is a straight line passing through the origin. This activity shows that the value of current varies linearly with the voltage. In other words, the ratio of V to I is a constant quantity. This is given in the form of a law which is called the Ohm's law. Statement. The electric current flowing in a metallic conductor is directly proportional to the potential difference across its terminals, provided physical conditions of the conductor such as length, area of cross-section, temperature, and material remain constant. If V is the potential difference across the conductor and I is the current flowing through it, then V is proportional to I. Hence, V upon I is equal to constant. This constant is the resistance R of the conductor. Hence, V is equal to IR. This is the mathematical form of the Ohm's law. The SI unit of resistance is ohm. It is denoted by symbol ohm. If a current of 1 ampere flows through a conductor when a potential difference of 1 volt is applied across it, then the resistance of the conductor is 1 ohm. 1 ohm is equal to 1 volt divided by 1 ampere. The unit for resistance, ohm, is used in honor of the scientist George Simon Ohm.
Resistance of different substances under similar physical conditions is different. Let us perform an activity to observe it experimentally.
Activity. Take wires of equal lengths and thickness made of different materials like copper, aluminium, and nichrome. Construct an electric circuit to measure current flowing through a wire and potential difference across it. Connect the copper wire in the gap AB using clips. Close the plug key and record the potential difference in the voltmeter and the current in the ammeter. It is 1.5 volt and 300 milliampere, which is equal to 0.300 ampere. Let us calculate the resistance of the copper wire using Ohm's law. V is equal to IR. Resistance of the copper wire RC is equal to V upon I, which is equal to 1.5 upon 0.3, which is equal to 5 ohm. Now let us connect aluminium wire and record potential difference across the wire and the current flowing through the wire. They are 1.5 volt and 185 milliamperes. Therefore, resistance of the aluminium wire RA is equal to 1.5 volt divided by 0.185 is equal to 8 ohm. Now, let us connect a nichrome wire in the circuit and record potential difference across the wire and the current flowing through the wire. They are 1.5 volt and 30 microampere. Therefore, resistance of the nichrome wire Rn is equal to 1.5 volt divided by 30 multiplied by 10 to the power minus 6 is equal to 50,000 ohm. Thus, we can conclude that the resistance of wires made from different materials with equal length and thickness have different resistance. Concept of resistance. We have seen that in metals, atoms are closely spaced. The free electrons in the metal move inside the metal in random directions, while the positively charged atoms, that is, the positive ions, are fixed at the atom sides. When some potential difference is maintained across the metallic conductor, these electrons get accelerated towards the positive potential. The electrons move with some drift velocity. While in the course of their journey, these electrons collide with other electrons and positive ions. Due to these collisions, the speed of the electrons decreases. This generates obstruction or opposition to their motion towards the positive terminal. The property of the conductor due to which it opposes the flow of the current through it is called resistance. It depends upon the nature and the size of the conductor. Some materials have low resistance and some have very high resistance. Accordingly, they are classified as conductors and insulators. Classification of conductors and insulators. On the basis of the resistance offered by substances to the flow of the current, they are classified into conductors and insulators. The substances which have very low electrical resistance are called conductors. Metals like silver, copper, aluminium have very low resistance and hence are good conductors. In good conductors, free electrons are available in large numbers for the flow of the current. The substances which have very high resistance are called insulators. In insulators, very few free electrons are available. Thus, a very low current passes through them. In other words, they offer a high resistance to the flow of the current. Rubber, wood, glass are good insulators.
Let us solve some numerical problems based on Ohm's law.
Numerical problems. 1. Find the current passing through a 3 ohm resistor if potential difference of 12 volt is applied across it. Solution. First, write the given data. Resistance R is equal to 3 ohm. Potential difference V is equal to 12 volt. Formula. According to Ohm's law, we have V is equal to IR. I is equal to V upon R is equal to 12 volt upon 3 ohm, which is equal to 4 ampere. Hence, the current flowing through a 3 ohm resistor, if a potential difference of 12 volt is applied across it, is 4 ampere. 2. Find the resistance of a conductor if 0.24 ampere current is passing through it and a potential difference of 24 volt is applied across it. Solution. Let us first write the given data. Potential difference V is equal to 24 volt. Current I is equal to 0.24 ampere. We will use Ohm's law to find the resistance of the conductor. The formula to be used is V is equal to IR. R is equal to V upon I. Substituting the given values of V and I, we get R is equal to 24 upon 0.24. R is equal to 100 ohm. Hence, the resistance of a conductor is 100 ohm.
3. Suppose the resistance of an electrical component remains constant while the potential difference across the two ends of the component decreases to half of its former value. What change will occur in the current passing through it? Solution. We know that according to Ohm's law, V is equal to I into R, where R is the constant of proportionality. Here, resistance of component is constant. So we can write V is directly proportional to I. Hence, potential difference and current are directly proportional to each other. Now it is very clear that if potential difference across the two ends of the component decreases to half of its former value, then the current flowing through it will also become half. Factors on which resistance of a conductor depends. Let us perform a simple activity to understand about the factors on which resistance of a conductor, factors on which resistance of a conductor depends. Let us perform a simple activity to understand about the factors on which resistance of a conductor depends. Let us take a thin copper wire of length L. Connect one of its end to the negative terminal of a battery. Connect its another free end to the positive terminal of battery through a switch and an ammeter. Now allow the current to pass through the wire by closing the switch. Note the current displayed by ammeter. Now open the switch and replace the copper wire by another copper wire having same thickness but length twice the previous wire, that is 2L. Again, note down the ammeter reading. Now replace the wire by another copper wire having larger cross-sectional area but length same as that in the first case, that is L. Take note of the ammeter reading. Now replace copper wire by a nichrome wire of same length and area of cross-section as in first case, and note down current flowing in circuit through ammeter. What do you observe? Is current flowing in the circuit same in all the cases? No. You will observe that when length of the wire is doubled, current flowing through it becomes almost half. Also, when area of cross-section of wire is increased, keeping its length same, current passing through it also increases. Even variation in current is observed on changing material of wire by keeping its length and area of cross-section same. From the activity, we can clearly say that current is inversely proportional to length of the wire. That is, I is proportional to 1 upon L. Also, current is directly proportional to the area of cross-section of the wire. That is, I is proportional to A. But according to Ohm's law, current is inversely proportional to resistance. That is, I is proportional to 1 upon R. Comparing above equations, we get R is proportional to L. Let us name it as equation 1. And R is proportional to 1 upon A. Let us name it as equation 2. Hence, we can say that resistance of a conductor depends on length of a conductor, area of cross-section of a conductor, nature or material of conductor. Combining equations 1 and 2, we get R is proportional to L upon A. That is, R is equal to rho into L upon A. Here, rho is the constant of proportionality and is called resistivity of the material of the conductor. In the equation, R is equal to rho into L upon A. That is, rho is equal to R into A upon L. SI unit of L is meter, that is M. SI unit of area is meter square, that is M square. While that of resistance is ohm. Hence, SI unit of resistivity is ohm meter. Resistivity is the characteristic property of the material. Metals and alloys have resistivity in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter, which is very low. Hence, metals and alloys are good conductors of electricity. On the other hand, resistivity of insulators is of the order of 10 to the power of 12 ohm meter to 10 to the power of 17 ohm meter, which is very high. Hence, insulators are poor conductor of electricity. Resistance R and resistivity rho both depend on the temperature of the material. Let us see electrical resistivity of some substances at 20 degrees Celsius. We can observe that resistivity of an alloy is higher than that of its constituent metals. Hence, alloys do not oxidize easily at higher temperatures and so are commonly used in electrical heating devices such as electric iron, electric heater, electric oven, etc. Let us now solve a numerical problem based on the topic we discussed.
If the length of a wire is 50 centimeter and radius is 0.5 millimeter, find the resistivity of the wire if its resistance is 30 ohm. Solution. Let us first write the given data in proper units. Length L is equal to 50 centimeters, equal to 50 into 10 raised to minus 2 meters. Radius R equal to 0.5 millimeter, equal to 0.5 into 10 raised to minus 3 meters, equal to 5 into 10 raised to minus 4 meters. Resistance R is equal to 30 ohm. We want to find the resistivity of the wire. The resistivity rho is related to the resistance R, length L, and area of the cross-section by equation. R is equal to rho multiplied by L upon A, 1. Rho is equal to R multiplied by A upon L, 2. Let us first find the area of the cross-section of the wire. As wire is cylindrical in shape, its area of cross-section is given as A is equal to pi r square. Therefore, A is equal to 3.142 multiplied by 5 multiplied by 10 to minus 4 on the whole square is equal to 3.142 multiplied by 25 multiplied by 10 raised to minus 8, which is equal to 78.55 multiplied by 10 raised to minus 8 meter square. Let us substitute the values of R, A and L in equation 2. Rho is equal to 30 multiplied by 78.55 multiplied by 10 raised to minus 8 divided by 50 multiplied by 10 raised to minus 2. Rho is equal to 47.13 multiplied by 10 raised to minus 6 ohm meter. Hence, the resistivity of the material of the wire, rho, is equal to 4.71 multiplied by 10 raised to minus 5 ohm meter.
Resistance of a system of resistors. In various electrical appliances, resistors are connected in various combinations. There are basically two different ways in which resistors can be connected. They are series combination and parallel combination. When number of resistors are connected end-to-end consecutively, then resistors are said to be connected in series. In this circuit, three resistors of resistances, say R1, R2 and R3, are connected end-to-end. An ammeter connected between plug key K and point A measures current supplied by the battery. A voltmeter is used to measure voltage across the resistors. In this type of connection, the same amount of current flows through each resistance. This type of joining of resistors is called as resistors in series. On the other hand, when number of resistors are connected in a way that they have common positive and common negative terminal, then resistors are said to be connected in parallel. Resistors of resistances R1, R2 and R3 are connected together in the circuit. The ammeters connected to resistors measures the current flowing through them. Here, current supplied by the battery is divided in the branches formed by the three resistors, but the potential difference across the resistors is same. This combination of resistors is called as resistors in parallel. Resistors in series. What will happen to the value of current if number of resistors are connected in series in a circuit? What will be the equivalent resistance of all the resistors in series? Let us obtain answers of these questions by performing a simple activity. Activity: connect three resistors of resistances, say 1 ohm, 2 ohms and 3 ohms end to end, that is in series. Now, connect them to a battery of 6 volts through an ammeter and a switch. Plug the key. Note down the current flowing in the circuit using ammeter. Now, unplug the key and change the position of ammeter in between the resistors. Again, note down the value of current. Change the position of ammeter one more time. What do you observe? Is there any change in the value of current flowing in the circuit? No. The value of current in the ammeter is same for its different position in the electric circuit. Hence, we can conclude that in a series combination of resistors, current flowing in every part of the circuit is the same.
Let us consider three resistors R1, R2 and R3 connected in series between points C and D, which are connected to a battery, and an ammeter through plug key K. Let I be the current supplied by the battery. In series combination, same current flows through each resistors. Let V be the potential difference between point C and D. Let V1, V2 and V3 be the potential differences across R1, R2 and R3 respectively. Hence, the total potential difference V gets distributed in V1, V2 and V3. Hence, V is equal to V1 plus V2 plus V3, 1. If Rs is the effective resistance in the circuit, then using Ohm's law, we can write P is equal to IRS. 2. Similarly, V1 is equal to IR1, V2 is equal to IR2 and V3 is equal to IR3. 3. Using 2 and 3 in 1, we have IRS is equal to IR1 plus IR2 plus IR3. 4. Therefore, RS is equal to R1 plus R2 plus R3. 5. For n number of resistors connected in series, RS is equal to R1 plus R2 plus R3 plus R4 plus up to plus Rn. This is the expression for effective resistance if resistors are connected in series. Let us note some important points. If the resistors are connected in series, then 1. The same current flows through each resistance. 2. The equivalent or effective resistance of the combination is equal to the sum of the individual resistances. 3. The total voltage across the combination is equal to the sum of the voltage across the separate resistors. 4. The effective resistance in series combination is greater than the individual resistances. 5. The resistances are connected in series to increase resistance in the circuit. Let us solve some numerical problems based on this. Numerical problems. 1. If 3 resistors, 20 ohm, 3.5 ohm and 4.9 ohm each, are connected in series, what is the effective resistance? Solution. Let us first write the given data. Given R1 is equal to 20 ohm, R2 is equal to 3.5 ohm and R3 is equal to 4.9 ohm. The resistances are connected in series. Hence, their effective resistance Rs is given by Rs is equal to R1 plus R2 plus R3 is equal to 20 plus 3.5 plus 4.9. Therefore, Rs is equal to 28.4 ohm. Hence, the effective resistance is 28.4 ohm. 2. If 6 ohm and 4 ohm resistors are connected in series, find the current in the circuit if a potential difference of 18 volts is applied across it. Also find the potential difference across each resistor. Solution. Let us write the given data. Given R1 is equal to 6 ohm, R2 is equal to 4 ohm and V is equal to 18 volt. Resistors are connected in series. Hence, the effective resistance is given by Rs is equal to R1 plus R2 is equal to 6 plus 4 is equal to 10 ohm. Let I be the current supplied by the battery. The series combination offers an effective resistance Rs. Hence, according to Ohm's law, we have V is equal to I multiplied by Rs. Therefore, I is equal to V divided by Rs. Substituting values of Rs and V, we get I is equal to 18 divided by 10 is equal to 1.8 ampere. This current flows through both the resistors. Let V1 and V2 be the potential difference across the resistors 6 ohm and 4 ohm respectively. Now, V1 is equal to I multiplied by R1. V1 is equal to 1.8 multiplied by 6. V1 is equal to 10.8 volt. Similarly, V2 is equal to I multiplied by R2 is equal to 1.8 multiplied by 4. V2 is equal to 7.2 volt. Therefore, the current in the circuit is 1.8 ampere and the potential difference across 6 ohm is 10.8 volt and 4 ohm is 7.2 volt. Let us consider parallel connection of resistors and find the effective resistance of the combination.
3. Draw a schematic diagram of a circuit consisting of a battery of 3 cells of 2 volts each. A 5 ohms resistor, an 8 ohms resistor, and a 12 ohms resistor, and a plug key all connected in series.
Find the potential difference and current across
12 ohms resistor. Solution. Here, 3 cells of 2 volts each form a battery which can be represented by drawing 3 cells connected in series, which is further connected to a resistor of 5 ohms, 8 ohms, and 12 ohms in series. Also, a plug key is connected in series to allow the passage of current whenever required. Let us now connect an ammeter in this circuit to measure current across the circuit and a voltmeter across 12 ohms resistor to measure potential difference across it. Here, the 3 resistors of 5 ohms 8 ohms and 12 ohms are connected in series. So, total resistance R is equal to 5 plus 8 plus 12 ohms is equal to 25 ohms. Potential difference V is equal to 6 volts. According to Ohm's law, V is equal to I into R. Therefore, I is equal to V upon R is equal to 6 divided by 25 is equal to 0.24 ampere. Since the current flowing in the circuit is 0.24 ampere, so ammeter will show 0.24 ampere current. We have calculated that a current of 0.24 ampere flows in the circuit. The same current of 0.24 ampere also flows through the 12 ohms resistor, which is connected in series. Now, for 12 ohms resistor, current I is equal to 0.24 amperes. Resistance R is equal to 12 ohms. Therefore, V is equal to I into R is equal to 0.24 into 12 is equal to 2.88 volts. Hence, potential difference across 12 ohms resistor is 2.88 volt. So the reading of voltmeter will be 2.88 volts. Resistors in parallel.
Effective resistance of resistors connected in parallel. Let us consider 3 resistors R1, R2 and R3 connected in a parallel between points C and D, which are connected to a battery, and an ammeter through plug key K. Let us connect ammeters to measure currents through R1, R2 and R3. The currents flow through the resistors and add to each other at point D to be equal to I. Let I1, I2 and I3 be the currents flowing through R1, R2 and R3 respectively. Therefore, we have I is equal to I1 plus I2 plus I3, 1. Let V be the potential difference between points C and D. Let I be the current supplied by the battery. In parallel combination of resistors, the current supplied by the battery gets divided in the branches at point C. Let Rp be the effective resistance in the circuit. From Ohm's law, we can write I1 is equal to V divided by R1. I2 is equal to V divided by R2. I3 is equal to V divided by R3 and I is equal to V divided by Rp. Using these values in equation 1, we get V divided by Rp is equal to V divided by R1 plus V divided by R2 plus V divided by R3, which can be written as 1 divided by Rp is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. For n number of resistors connected in parallel, we get 1 divided by Rp is equal to 1 divided by R1 plus 1 divided by R2 plus up to 1 divided by Rn. Let us note some important points. If the resistors are connected in parallel, then the voltage across each resistor is the same. The sum of the reciprocals of the individual resistance is equal to the reciprocal of the effective resistance. The total currents flowing through all resistors connected in parallel is equal to the sum of currents flowing through individual resistors. The currents flowing through various resistors are inversely proportional to the resistances. Higher is the resistance, lower is the current through it. The effective resistance of combination is less than the individual resistances in the combination. The resistances are connected in parallel to decrease resistance in the circuit. Now, we are in position to differentiate between resistance in series and in parallel. When resistors are connected in series, same current flows through each resistance. On the other hand, when resistors are connected in parallel, the voltage across each resistor is the same. For resistors connected in series, the equivalent or effective resistance, Rs, is equal to the sum of the individual resistors. For n resistors connected in series, Rs is equal to R1 plus R2 plus R3 plus R4 plus up to Rn. Resistors connected in parallel, the sum of the reciprocals of the individual resistance is equal to the reciprocal of the effective resistance, Rp. For n resistors connected in parallel, 1 divided by Rp is equal to 1 divided by R1 plus 1 divided by R2 plus up to 1 divided by Rn. The effective resistance in series combination is greater than the individual resistance. The effective resistance of parallel combination is less than the individual resistance in the combination. The total voltage across the series combination is equal to the sum of the voltage across the separate resistor. The total current flowing through all resistors connected in parallel is equal to the sum of currents flowing through individual resistors. Let us solve some numerical problems on the topic. Numerical problems. 1. Three resistances, 1 ohm, 2.2 ohm and 3.9 ohm are connected in parallel. Find the effective resistance of the circuit. Solution. Let us first write the given data. Given. R1 is equal to 1 ohm, R2 is equal to 2.2 ohm, and R3 is equal to 3.9 ohm. The resistors are connected in parallel. The effective resistance of the parallel combination is given by 1 divided by Rp is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Substituting the given values of R1, R2 and R3 in the equation, we get 1 divided by Rp is equal to 1 divided by 1 plus 1 divided by 2.2 plus 1 divided by 3.9. Taking LCM of the denominator, we can write 1 divided by Rp is equal to 2.2 multiplied by 3.9 plus 2.2 plus 3.9 divided by 2.2 multiplied by 3.9. 1 divided by Rp is equal to 14.68 divided by 8.58. Therefore, Rp is equal to 0.58 ohm. The effective resistance of the circuit is 0.58 ohm. 2. If the resistors 5 ohm, 10 ohm and 30 ohm are connected in parallel to a battery of 12 volt, find the effective resistance of a circuit. Calculate the total current and the current in each resistor. Solution. Let us first write the given data. R1 is equal to 5 ohm, R2 is equal to 10 ohm and R3 is equal to 30 ohm and V is equal to 12 volt. The resistors are connected in parallel, hence the effective resistance of the circuit is given by 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Substituting the given values of R1, R2 and R3 in the equation, we get 1 divided by Rp is equal to 1 divided by 1 plus 1 divided by 2.2 plus 1 divided by 3.9. Taking LCM of the denominator, we can write 1 divided by Rp is equal to 2.2 multiplied by 3.9 plus 2.2 plus 3.9 divided by 2.2 multiplied by 3.9. 1 divided by Rp is equal to 14.68 divided by 8.58. Therefore, Rp is equal to 0.58 ohm. The effective resistance of the circuit is 0.58 ohm. 2. If the resistors 5 ohm, 10 ohm and 30 ohm are connected in parallel to a battery of 12 volt, find the effective resistance of a circuit. Calculate the total current and the current in each resistor. Solution. Let us first write the given data. R1 is equal to 5 ohm, R2 is equal to 10 ohm and R3 is equal to 30 ohm and V is equal to 12 volt. The resistors are connected in parallel, hence the effective resistance of the circuit is given by 1 upon
Chemical reactions taking place within a cell or a battery helps in moving electrons, that is, in generating current within a circuit. To maintain current in the circuit, source needs to spend energy continuously. You might have observed that electric fan becomes hot when used for longer time. But what will happen if an electric circuit is purely resistive? Well, energy of the source will be continuously dissipated in the form of heat. This is the heating effect of electric current. Let us explore in detail the heating effect of electric current by studying Joule's law.
Joule's law. Heat produced in a current-carrying conductor. Let us consider a potential difference V applied to a conductor of resistance R. The current flowing through it is given as I is equal to V upon R. Let the current be passed for time t. Therefore, the charge flowing through the conductor is Q is equal to IT. Now, the potential difference is the work done in circulating a unit charge in the circuit. Therefore, the work done W by the potential difference of V in circulating charge Q is W is equal to BQ. Using V is equal to IR and Q is equal to IT, we can write W is equal to IR multiplied by IT. W is equal to I square RT, or W is equal to VIT. When current flows through a conductor, work is done to overcome the resistance offered by the conductor to the flow of the current. This work done is converted to heat. Hence, W is equal to I square RT joule. This is the amount of heat generated in the conductor. Heat is generally expressed in heat units, that is, in calorie. The relation between joule and calorie is 4.18 joule is equal to 1 calorie. Hence, heat produced in a conductor in terms of calories is given by H is equal to I square RT divided by 4.18 calories. This is put in a law by scientist James Prescott Joule. Joule's law statement. According to Joule's law, the quantity of heat generated H in a conductor of resistance R when a current I flows through it for a time t is directly proportional to 1. The square of the current, 2. The resistance of the conductor, and 3. The time for which the current flows. Joule's law in equation form is written as H is equal to I square RT divided by 4.18 calories. Using Ohm's law, we can write H is equal to V square T upon 4.18 R calories, or H is equal to VIT upon 4.18 calories.
Practical applications of heating effect of electric current.
Electric bulb. The electric bulb consists of a filament made up of tungsten. The tungsten filament is supported on nickel, iron, lead wires, which are soldered to the stem of the bulb. The bulb is filled with chemically inactive gases like nitrogen and argon at lower pressure. These gases prevent the oxidation of the filament and prolong its life. Tungsten has been chosen as a filament material because it has a very high melting point of 3380 degrees Celsius. It has a very high resistance also. When current is allowed to pass in a bulb, the temperature of the tungsten filament rises to 2000 degrees Celsius. At this temperature, it becomes white hot and starts giving off light. It does not melt when it is white hot. Electric fuse. When large amount of electric current flows through any electrical appliance, it can overheat the wires present inside the appliance. This can cause damage to the appliance. In order to protect electric circuits and electrical appliances against excess flow of current, a safety device called a fuse is used. Let us understand the working of an electric fuse. An electric fuse is used to protect electric circuits and electrical appliances against excess flow of current. The fuse is a thin wire made up of solder, a tin lead alloy, which is 60% tin and 40% lead, that has high resistance and low melting point. The fuse wire is usually enclosed in a cartridge of porcelain or similar material with metal ends. It is connected in series with a device or circuit to be protected. When a large current exceeding the safe limit passes through the device or the circuit, the fuse wire melts and the circuit breaks. This protects the device or the circuit from excessive current. The fuses with current ratings of 1 ampere, 2 amperes, 3 amperes, 5 amperes, etc. are generally used in household appliances.
While using an electric heater, have you ever thought that why does the cord of an electric heater not glow while the heating element does? Well, the heating element of electric heater is made of nichrome, which becomes red hot due to the large amount of heat produced on passing current because of its high resistance. But the cord or connecting cable of the heater made of copper does not glow because negligible heat is produced in it on passing current because of its extremely low resistance. Let us solve some numerical problems based on the heating effect of current.
Numerical problems. 1. Two dissimilar bulbs are connected in series. Which bulb will be brighter? Solution. Let us consider a circuit in which two dissimilar bulbs are connected in a series. Can you tell which bulb will be brighter? Let the resistance of the first bulb be greater than the second bulb. As the bulbs are connected in series, the same amount of current will flow through them. The heating of the filament of the bulb is proportional to the resistance, hence, the bulb with a higher resistance, that is, the first bulb here, will glow brighter. 2. Find the heat generated in calories. If a current of 0.2 ampere is passed through a coil of resistance 418 ohm for 1 minute. Solution. Let us first write the given data in proper units. Given current I is equal to 0.2 ampere. Resistance R is equal to 418 ohms and time T is equal to 1 minute is equal to 60 seconds. According to Joule's law, the heat H generated because of the current I passing through a resistance R for a time interval T is given by H is equal to I square RT divided by 4.18 calories. Therefore, H is equal to 0.2 square into 418 into 60 divided by 4.18. Therefore, H is equal to 240 calories. Hence, the quantity of heat generated in calories if a current is 0.2 ampere is passed through a coil of resistance 418 ohm for 1 minute is 240 calories. 3. A potential difference of 250 volts is applied across a resistance 1000 ohm in an electric iron. Find 1. The current and 2. Heat energy produced in joules in 12 seconds. Solution. Let us first write the given data. Given potential difference V is equal to 250 volt. Resistance of the iron R is equal to 1000 ohm. Time interval T is equal to 12 seconds. Let us first find the current flowing through the resistor using Ohm's law. That is, I is equal to V divided by R is equal to 250 volt divided by 1000 ohm, which is equal to 0.25 ampere. Now, the heat produced is given by the Joule's law. H is equal to I square RT joule equal to 0.25 square multiplied by 1000 multiplied by 12 is equal to 750 joule. Electric power. On the electric bulbs is written 60 watt, 100 watt, etc. This is the electric power rating of the bulbs. Similarly, every electric device is characterized by power settings. Let us see what it is meant by electric power and how it is used. We know the rate of doing work is called power. That is, power is equal to work divided by time. Electric supply or the battery do the work of circulating current in the circuit. Similarly, electric power is the electrical work done per unit time. In other words, the rate at which electrical work is done is called electric power. Electric power is also defined as the rate at which electrical energy is consumed. Let us define the unit used to measure electric power. 1 watt power. The SI unit of electric power is watt. It is denoted by symbol W. If 1 joule of work is done per second, then the electric power is 1 watt. 1 watt is equal to 1 joule divided by 1 second. A bigger unit kilowatt is used for commercial purpose. It is defined as 1 kilowatt is equal to 1000 watt. Let us find expression for electric power. We know if W is the work done in time t, then power P is given by P is equal to W upon T. But W is equal to VIT. P is equal to VIT divided by T. P is equal to VI. Thus we get electric power is equal to voltage multiplied by current. Using Ohm's law, P is equal to IR. We can write P is equal to I square R. Let us define the commercial unit used for electrical energy consumed. The commercial unit of energy is taken as kilowatt hour. It is commonly known as unit. It is the amount of electric energy consumed in 1 hour by an appliance of 1 kilowatt. Hence, 1 kWh is equal to 1000 watt multiplied by 3600 seconds is equal to 3.6 multiplied by 10 raised to 6 watt second. What is watt second? We have defined 1 watt is equal to 1 joule divided by 1 second. Hence, 1 watt second is equal to 1 joule. Therefore, 1 kilowatt hour is equal to 3.6 multiplied by 10 raised to 6 joule. Let us solve some numerical problems. Numerical problems. 1. If a bulb of 60 watts is connected across a source of 220 volt, find the current drawn by it. Solution. Let us first write the given data. Given power P is equal to 60 watt. Voltage V is equal to 220 volt. The power is given by P is equal to VI. Therefore, I is equal to P divided by V is equal to 60 watt divided by 220 volt is equal to 0.2727 ampere. 2. An electric bulb is connected to 250 volt. The current is 0.27 ampere. What is the power of the bulb? Solution. Let us first write the given data. Given voltage V is equal to 250 volt and current I is equal to 0.27 ampere. The power rating of the bulb is given by P is equal to VI. Substituting given values of V and I, we get P is equal to 250 multiplied by 0.27. Therefore, P is equal to 67.5 watt. Therefore, the power of the bulb is 67.5 watt. 3. If a TV of rating 100 watt operates for 6 hours per day, find the number of units consumed in any one leap year. Solution. Let us first write the given data. Given power rating of the TV, P is equal to 100 watt. Time interval of daily operation, 6 hours. Number of days in a leap year is equal to 366 days. The electric energy consumed is given by energy consumed is equal to power multiplied by time. Energy consumed is equal to 100 multiplied by 6 multiplied by 366 is equal to 2,19,600 watt hours is equal to 219.6 kilowatt hours is equal to 219.6 units. 4. An electric iron rated 750 watts operates 2 hours a day. If the cost of 1 unit is 3 rupees per kilowatt hour, find the cost of energy if we have to operate the electric iron for 30 days. Solution. Let us first write the given data. Given power rating of the iron, P is equal to 750 watt. Time interval of daily operation, T, is equal to 2 hours. Number of days is equal to 30 days. The electric energy consumed is given by energy consumed is equal to power multiplied by time. Energy consumed is equal to 750 multiplied by 2 multiplied by 30 is equal to 45,000 watt hours is equal to 45 kilowatt hours is equal to 45 units. Therefore, the cost of electricity is 3 rupees per unit. Total cost of energy is equal to 45 into 3 is equal to 135. Therefore, the cost of energy is 135 rupees. 5. A washing machine rated 300 watts operates 1 hour per day. If the cost of 1 unit is 3 rupees, find the cost of energy to operate the washing machine for the month of March. Solution. Let us first write the given data. Given power rating of the washing machine, P, is equal to 300 watts. Time interval of daily operation, T, is equal to 1 hour. Number of days of the month, March, is equal to 31. Energy consumed is equal to power multiplied by time. Energy consumed is equal to 300 multiplied by 1 multiplied by 31 is equal to 9,300 watt hours is equal to 9.3 kilowatt hours is equal to 9.3 units. The cost of electricity is 3 rupees per unit. Therefore, total cost of energy is equal to 9.3 multiplied by 3 is equal to 27.90 rupees. Therefore, the cost of energy to operate the washing machine for the month of March is 27.90 rupees.